Welcome everyone to the third day of our workshop. The first speaker of our morning session is Dr. Xin Wang from KIAS here in Seoul, and he's going to talk to us about quantum periods and spectra in diamond models and Calabi-Yau geometries. Please go ahead, Xin.
Okay, so I would like to first thank Rak for inviting me to give this talk. As Rak has been introduced, I will talk about the quantum periods and the spectra in diamond models and Calabi-Yau geometries. So this topic comes from this, the sequence of connections. I'm interested in the topological string theory on, for example, Calabi-Yau threefolds. And in this talk, I will mainly focus on the toric Calabi-Yau threefolds. And if you compactify the M theory on this toric Calabi-Yau threefolds, you will in principle get a 5D, at least this is a non-compact Calabi-Yau threefolds, you will get a 5D X1 gauge theory with a gravitational sector decoupled because of the non-compact Calabi-Yau. And the BPS partition function of the M theory compactification of the 5D gauge theory is also captured by the free energies or amplitudes of the topological strings here. And the well-known subject to the 5D N=1 gauge theory is that we have the so-called Seyberg-Witten curves, and this is equivalent to the B-model mirror curve because of the correspondence. So it turns out that this Seyberg-Witten curve or the B-model mirror curve is a spectral curve of some kinds of, from the 5D gauge theory, it's a relativistic version of the, for example, for TODA system, for the A-type SUN gauge theory, and that integral system, in other hand side can be described by the, has a more generic generalization by the, so-called cluster integral system for diamond models, torus. And initially, this cluster integral system or the dimers or the Brine-Tilings comes from the 4D X1 gauge theory. And from that description, we can maybe map to, connect to the cluster integral system. And my goal today is to study the spectra, or I would say the quantum spectra of the integral system. I would like to mention the binary model and the Brine-Tilings because purely from the 5D gauge theory side or the topological string side, you are naturally get the spectral curve of the integral system. But in order to study the spectrum, you need to know knowledges about the full form of the Hamiltonians, which is not that direct to get it from the 5D, X1 gauge theory side. But it tells that this Brine-Tiling and the dimers naturally gives a description how to get the Hamiltonians from the construction of cluster integral system. I think that is initially invented by, including one of our speakers last day, the KIAS paper in 2011. My outline of this talk is basically like this. I will first introduce the topological strings on toric Calabi-Yau threefolds, and I will say how to get the functional difference operator, which is the so-called spectral quantized spectral curve of the quantization of the mirror curves. And for higher genus, I will say try to connect it to the cluster integral system for diamond models on torus. And on the third day, I will give comments. Maybe this is not my main topic, but I will give a comments on the so-called exact quantization condition. And in the last, I will give comments on the non-toric cases. A toric Calabi-Yau threefolds is usually referred to the local Calabi-Yau threefolds, which is a local limit of an elliptic fiber Calabi-Yau threefold. In the large elliptic fiber limit, we get a non-compact Calabi-Yau threefold, where the local mirror symmetry is induced from the mirror symmetry for a hyper surface Calabi-Yau manifold in the higher dimensional toric embedding in the higher dimensional toric varieties. And the mirror geometry in the B model is a hypersurface. Usually, is in particular for the toric Calabi-Yau manifold, is a hypersurface written in such a form. And this hypersurface could be regarded as a UV fibration over the this Riemann surface. Illustrate that here. As you may already seen from the expression of the B model geometries, one can naturally define a holomorphic three form in like this. To say why this is holomorphic, because around u equals 0, there will be a pose, but you can convert it to the v parameters. So this is still no pole. And anywhere in the Calabi-Yau space. So this is indeed a holomorphic three form. And the integration over a three cycle of the holomorphic three form is a period. And this period is reduced to the integral over a disk. If you first integrate out this integrate over the u equals 0 plane, such that you will get such a expression for the period, and you can further map to the in this form, and this partial d becomes a curve inside this Riemann surface, defined from the 0 values of for example, u equal to 0, like this. And this p dx becomes a meromorphic one form of the Riemann surface. And this algebraic and this sigma becomes an algebraic curve, and is usually called a mirror curve. The reason we call it mirror curve instead of mirror hypersurface, because you could already see that all the information of the periods is encoded in the periods of the Riemann surface of the curve. So for local Calabi-Yau manifold, the simplest thing that we can simply study the periods of the curve that we can recover the information of the Calabi-Yau periods. And maybe for torus, there are usually two non-trivial cycles. One is over this direction. Usually we call this A cycle. And another cycle would be in this direction. It's usually called B cycle. And the integration over these two non-trivial cycles gives the so-called A and B periods. And this induced, it's the induced period from the Calabi-Yau periods. For a toric Calabi-Yau threefold, which is a topological line bundle over a toric surface, and this toric surface is usually described by ray vectors in the two-dimensional space. Let's give a concrete example. So this is a toric surface of local P1 times P1. To be honest, this is a 3D version of the local of P1 times P1. So this is a P1 and another P1. And the vector of this three-dimensional toric diagram is described by such a vectors. This is a 0, 0, 0, 1, 0, 0, 1, 0, minus 1, minus 1, 0. And I just call this two-dimensional coordinates by nu I. So from the standard construction of the mirror manifold, we can easily write down the expression for the Riemann surface in such a form. where the AI is a homogeneous coordinates construction for the toric variety. And you could regard it as a complex structure parameter because not all of them are independent. So for example, for local P1 and P1, we can simply, make 3 of them to be 1. So to be honest, the 4th one will contain another mass parameter, but I just omitted it. So I finally could have a expression for the mirror curve for local P1 times P1. And U is the only non-trivial compact structure parameter due to the compact divisors, which is denoted by this line. So this DU is defined from this hyperplane as a divisor. I'm interested in the quantization of this spectral curve, of this mirror curve. A typical way to do the quantization is to do the canonical quantization by promoting this non-commutation relation by making X and P to be operators and make them non-commutative. And this will naturally lead to an quantum curve where all the coordinates become non-commutative and Hamiltonians or the homogeneous coordinates becomes a quantum Hamiltonians. I denote it as H hat. And the whole equation becomes a difference operator. So you can somehow define the wave function, makes a difference operator act on it. And this I partial H bar partial X is a representation for the from this commutation relation. So this is a maybe standard quantum mechanics notations I used. And I use this N to denote the different energy levels. From the point of view of quantum operators, difference operators, this psi x is the nth eigenfunctions, and Hn is the nth eigenvalues correspond to the eigenfunctions. So the reason we have discrete eigenvalue because the phase volume of this described by this quantum mechanics is finite, as I will illustrate it later. And to compute the spectrum of the Hamiltonians explicitly or perturbatively, one can do the perturbative expansion by expand H hat and P hat in such a form. Further, we can connect it to the harmonic oscillator by introducing the creation and annihilation operators A and A dagger, and then we use the property of the harmonic oscillators and treat it as a perturbation of the harmonic oscillator. We can actually solve the Hamiltonian as a function of the energy level N. So this can be done perturbatively when H bar is very small. And the most famous method in studying quantum mechanics is the so-called Wkv method. And you can actually define the wave function psi in terms of such a function, exponential of Sx. And the Wkv expansion indicates that this function S has a H bar corrections expansions, and with a leading term to be the phase volume of the classical quantum mechanics. And this volume, no, that's not the phase volume, but connect to the phase volume. So the phase volume is described by the dp dx over a fixed region. And this region, for example, this region is described, illustrated in this graph. so you could see already seen that this region is bounded. That's why the energy level is discrete. And by performing this integral, you could finally find a formal expression where the P plus X is a region along this part, and the P minus is region along this side. And this gives a area integral. I mean, compute the area of the whole space, free space like this. So from the description above, we can also compute the quantum phase volume. In analogies with the Wkv expansion, the phase volume also have a similar h bar expansion, only in terms of the h bar even order, and where the big H inside is a so-called quantized eigenvalues. So I ignore the quantum level n, but there should be an n over here. So by embedding this quantum eigenvalues into the form, you could in principle get such a h bar expansion for the phase volume, quantized phase volume. And also in the standard quantum mechanics technique method, maybe textbook, you could find such a phase volume is actually quantized. And the quantization condition is described by the Bohr-Sommerfeld quantization condition, which means that the volume of H is the volume of space depend on, as a function of H is actually quantized at 2 pi h bar n plus 1/2. And this 1/2 maybe is also well known as the Wkv corrections in the quantization condition. So everything I have mentioned is just the standard quantum mechanics techniques. Why I'm trying to say that? Because there's a natural map between the quantum mechanics and the quantum geometries. The map is that the quantum spectrum in the quantum mechanics is mapped to the quantum complex structure parameters in the quantum geometry, in particular the B-model geometry. And the quantum phase volume is mapped to the quantum B pairs in the quantum geometry. To be honest, I use the quantum geometry because in particular, that is a quantization of the topological strings. I would say higher generous corrections of the topological strings on toric Calabi-Yau threefold, but here I must use the refinement of it. So a refined topological string on Calabi-Yau threefold actually captures the BPS states of M2 branes running on holomorphic 2 cycles in the Calabi-Yau threefold. And the BPS partition function is written as exponential of the topological string amplitudes F. And by using the geometry engineering, you can engineer the so-called gauge theory from the geometry by looking at the singularity of the geometry. And this usually corresponds to 5D X1 gauge theory on R4 times S1, or even non-Lagrangian theory like local P2. And from M theory perspective, from M theory compactify on the Calabi-Yau threefolds. So this 5D gauge theory can be rigorously defined from the integral of K-theoretical equivariant cohomologies with equivariant parameters epsilon1, epsilon2. And these two parameters in physics is treated as a graviphoton field strings. And in the topological string theory, it can be regarded as a refinement of the string couplings. And as was well known that the 5D X1 gauge theory is connected to the Seyberg-Witten curve, where the pre-potential of it is captured by the periods of the Seyberg-Witten curve. And thanks to work of Nekrasov and Shabdashvili, we have a so-called a gauge and bat correspondence, such that if we quantize the Seyberg-Witten curve, this quantized Seyberg-Witten curve also connect to the gauge theory in a particular limit when by setting epsilon 2 to be 0 and epsilon 1 to be IH bar. And this limit is also usually called Nekrasov-Shadashvili limit, or simply NS limit. And the free energy defined in this way is usually called NS free energy. So let me give more clear map from the 5D gauge theory to the topological string theory. So in the gauge theory side, the Coulomb parameters is mapped to the gauge parameters in the is mapped to the Kähler parameters in the topological string theory, and the equivariant parameters epsilon 1, epsilon 2 is mapped to the refinement of the analogies of the string couplings, and the Seyberg-Witten curve is mapped to the mirror curves, and the so-called quantization condition from the bad gauge correspondence is mapped to the quantization of the B pairs, and all of them have a connection. The Seyberg-Witten curve and mirror curve are also the spectral curve of a so-called quantum integral system, if we do the quantization of it. And the phase volume I mentioned is identified with the partial T derivative of the NS free energy. I think this is a main statement in one of the main statement in Nekrasov and Shadashvili paper. So so for higher generous mirror curves, as I already mentioned, this integral system becomes a multi-particles integral system of multi-particles with multi-Hamiltonians. And the Sommerfeld quantization is naturally extended to this way. Here I add some metrics to make it more clear in the higher generous extension. But from the topological string theory or the 5D gauge theory, we may only naturally get the spectral curve. And the spectral curve of the cluster integral system for diamond model on torus is indeed the spectral curve we have already mentioned. But in order to study the spectrum with better move to the explicit description for the Hamiltonians, so that's why I just go to the I studied the diamond models. Basically I just use the description from diamond models and the integral system from that. So maybe this has already been mentioned by many speakers in talks last 2 days. But I still better have a review on it. For example, even though I don't talk about the 4D on-square quiver gauge theory, but this this quiver diagram are indeed the quiver diagram arises from the 4D on-square gauge theory, quiver gauge theory. I think interestingly that this quiver theory is related to the toric diagram, because this is the old story, but you start from a quiver diagram and you make it planar by expanded on periodically on a plane, and then do the dual graph, and this will naturally give the diamond models or the brane tilings. And the so-called diamond model is that we have a bipartite graph, which means this graph is a collection of black and white points, and they're connected by edges. The property of it is that if you find a black point inside, only white points can be connected to them. and vice versa. And from this dynamic model, from this dynamic model, you can define the custom matrix, and the spectrum, the determinant of the custom matrix is identified with the spectral curve. I mean, of the mirror curves I have already mentioned, and then we can identify with the toric diagrams by reading the the structure of the curve. And I think the dynamic models is also some kinds of starting of the perfect matchings. And the perfect matching is such kind of matchings that you draw the lines between the white and black dots. Or the points. And you draw such kind of set of lines such that this set of lines connect to all the black and white dots only once. So this set of lines is called and this set of lines do not intersect with each other. And this set of lines is called perfect matching. And the loops are generated from the difference of two perfect matchings. For example, this is a YP0 toric diagram, and this is one of the perfect matching for it. This figure is from the paper by Igor, Franco, and Schaffer. I think they're, Franco speak audience here. Maybe another example, I would say how to draw the loops. This is a diagram for Brentilians for this toric diagram. In the first figure, I draw. This is periodic in this direction. So this is the fundamental region of it. So these two dots are identified. So we can draw the perfect matching in three different ways. I denoted by three different colors. The first is red, and the blue and green. So by performing the difference between them, we can actually find there are 6 loops. I call this as a loop because these points and these points are identified. So this is the 1, 2, 3, 4, 5, 6. And with all the definition for the dynamic models, we can now introduce the integral system. And this is a notation from Goncharov and Rak-Kyeong. And their definition that for loops, for any 2 loops, omega I and omega j, we could define a Poisson bracket in this way. And with a coefficient epsilon is defined like this, where the delta V it can be, and where the sign V is positive is if the for example, if the points, if the dots is black, and if it become negative if the dot is black, is white. So this epsilon omega I omega j is defined by summing up all the combinations of the overlapping vertices. So I denote V as the vertices. If the overlapping vertex are in such a pattern, then the delta V omega 1 omega 2 is minus 1/2. If it is in such a pattern, reversely, we define their delta V to be 1/2. And if they're in such a pattern by putting the blue and white inversely, it's again the sign is flipped by 1, so it gives 1/2. So finally, with these rules, with all the 6 loops I have already mentioned, and you can actually write down the Poisson brackets for the loops. Maybe let's see why it works, because first thing is T1, T6 is overlapping at, for example, T1, T6 is overlapping at 1 and 10. So this dot is black and this dot is white. This is the T1 and T6. So the sign, the overall sign here is 1 minus 1/2 and minus 1/2 totally contribute to -1 over here. And the Hamiltonians then is then defined as a collection of n loops. For example, H1 is a collection of one loops, and is a purely simply the summation of 6 independent loops. And H2 is a summation over is a collection of 2 loops. For example, this T1 and T3 does not intersect, so we can put it here, and so-called the same for T1 and T4, etc. By collecting all of them, you get the second Hamiltonian H2. And the third one is actually not Hamiltonians. It's a Casimir related to the instant counting parameters in the gauge theory, or the mass parameters in the in the topological string language. And from the Poisson bracket, you can actually redefine using they're not independent, so you can actually introduce only 4 of 2 Q1s and the 2 Qs and another 2 Ps to make the commutation Poisson bracket holds. And further, you can do the quantization by replace the Poisson brackets to commutation relations such that you get the quantum Hamiltonians. And similarly, we do the productive expansion for it. We could compute the eigenvalues productively from H bar corrections. Depends on the 2 eigen energy level N1 and N2. And this is again agree with the quantum BPR's calculations from the, for example, the definition of net crossover shadow should be free energies. So you can also do the exact quantization condition. So the reason that the numerical calculations result shows that the eigenvalues of Hamiltonians operator does not agree with the Boole-Sommerfeld quantization condition when H bar is not small. So this guy probably is not accurate. So to cure this problem, the authors introduce a so-called non-productive completion of it, which is still like a transformation of the original as free energy. And by using this quantization condition, we can actually compare with the numerical values, and it agree with the numerical values perfectly, even at a large H, I would say not small H bar. So that S duality is almost a trivial, conclusion from such a observation. So for example, you start with a quantum curve. You can do such a kind of operation. And then you can compute the, using the Wkv method, you compute the S function. And this is actually equivalent to the S function in this, for this curve. And again, this commutation relation is again the same as the commutation relation over here. So we did nothing between these two transformations. We just indicated that the eigenvalues or the quantitative conditions, some things like that, also have the SDO-like transformation. But purely speaking, this guy do not have a SDO-like invariance. So the natural idea is that to make another piece of it to make it complete. And this is actually the correct answer people has already tried years ago. So let me give some open questions to the non-toric case. So thanks to the connection to the 5D gauge theory, we can actually introduce Hall-BPS defect in the gauge theory, and the quantum curve can be X-ray derived or partially derived and checked for many other non-toric cases. For example, the pure gauge theory with classical Lie group beyond A-type. So this is a D-type quantum curve that can be derived from the defect partition function. So you could already imagine that this curve still looks like a quantum curve for toric diagram, but it's slightly different. And also you can for SU2 with maybe 5, 6, 7, 8 flavors, the diagram, we still don't have a toric-like description when we turn all the mass parameters. In particular, for E string, the quantum curve is known as the elliptic Fine-Dijon operator. And it is interesting to see how do we get this integral system from from the diamond models, and how do we generalize it. On the other hand side, from the local limit, as I already mentioned, that for the toric Calabi-Yau threefolds, it's a local limit of elliptic fiber Calabi-Yau threefolds, and also from the local limit of Calabi-Yau threefold, elliptic fiber Calabi-Yau threefold, we can indeed define, have a toric description for this non-toric case. But it's a little bit different. So, for example, I give this is a toric embedding for the Calabi-Yau threefolds of 5D pure C2 or SP2 gauge groups. And but the sad thing is that we do not have a curve, but we have a hypersurface. As a B model geometry, different from the A type. It's not so easy to to find out easy description as some vibration over a Riemann surface. But it is indeed very easy to extract the Sibir-Witten curve classically by studying the singular behavior of this hypersurface. Maybe right. But I believe that operation break many the quantum information. So that information may not give the quantum curve. But due to the connection to gauge theory, we indeed have the quantum curve for this SP2 pure gauge series. So what is a maybe possible diamond model for it? I think this is a quite interesting question. I believe in the talks in last 2 days, there are many interesting generations to the diamond models. Maybe some of them are connect to the story over here. Okay, maybe it's time. So maybe is there any questions? Or thank you for the listening.
Yeah, thank you very much for the interesting talk, Xin.